Hello guys, in this video we are going to discuss the mathematics that is required for problem solving. So we'll be discussing the primality testing and sieve of Eratosthenes, GCD, binary exponentiation, modular arithmetics, combinatorics. The way I'll be teaching is firstly I'll define the theory or the concept behind each of these topics, and then we'll move to the CPP implementation of it. If you are using some other languages, it's completely fine. The implementation is somewhat gonna be the same. The only difference could be of syntax, and that you guys definitely can manage. However, for combinatorics, I already have a detailed video on this channel. I'll put the link of that video in the description section and also on the I button above. So make sure you watch that video before you start with this particular video. So with that, let's get started with primality testing. So what is primality testing? Let's call it PT. So primality testing is basically checking if a number is prime or not. So check if number is prime. But for that, what are prime numbers? I hope most of you know what prime numbers are, but for those who don't, a number, let's say n, is called prime if it only has two factors, that is 1 and n itself. So for example, 5 is a prime number, it only has two factors, 1 and 5. However, 6 is not a prime number, it has many factors, 1, 2, 3 and 6. So since it has more factors than 1 and 6 itself, so it's not a prime number, it's a composite number. Cool. With that, how can we test if a number is prime or not? A very naive way of doing it would be to check for all the numbers from 2 to n minus 1, right? I'll run a loop from 2 to n minus 1 and I'll check if, let's call this number x. So if n divided by x gives me a 0 remainder, or the modulus of n mod x is equal to 0, in that way I can say that okay, x is dividing n, so it has at least more than two factors, because 1 and n are always the factors of it. So more than two factors exist, and we can directly say that it's a composite number. If after checking for all of these numbers we are not able to find any factor which is dividing in, then we can say x is a prime number, right? Okay, so the complexity of this would be, for any number n we'll have to try for all the possibilities from 2 to n minus 1. So the complexity would turn out to be order of n. I hope that's making sense. Now, is there a way to reduce this complexity? Yes, we can easily do it in order of root n also. Now there are better ways of doing it, you can read about them, but order of root n would work for most of the cases. So how do we do it in order of root n? Let's take a big number, not a very big number, but let's say 64, right? Let's talk about the multiple factors of 64. So there are 1, 2, 4, then 8, then okay, so there are going to be some other factors as well. For example, one factor would be 16, right? I hope I'm not mistaken. Okay, 60 multiplied with this, 2 multiplied with 32. Yeah, so these are the factors of 64. So what I can say is that for these factors I only need to check up till root of 64. So the root of 64 is actually 8, right? So I'll only be checking for these elements. So for any number I'll only be checking up from 2 till root n. Now why is this the case? Because till root n, whatever number is coming, it actually needs to be multiplied by something that is greater than root n. So for example, over here, okay, over here we were multiplying 4 by 16, we were multiplying 2 by 32, we were multiplying 1 by 64, right? So the counterpart, or the number from 2 to root n, is actually multiplied by another number that is from root n plus 1 till n itself, or root n till n itself, right? Over here 8 was actually getting multiplied by itself. So this method will always get followed. So if there are no elements or there are no divisors in 1 to root n, right? If there are no divisors in 1 to root n, there are going to be no divisors in root n to n also. So checking only from 1 to root n is sufficient enough. So with that, what you can say is, in order to check the primality testing, we can run a loop from 1 or from 2, because 1 is always a factor, from 2 to root n, and check if, let's call it x, check if x is a factor. If it is a factor, then we'll return false or return composite number. If the loop however completes and we were not able to find any factor, then we can return a prime number. In this way we can complete this check in order of root and time complexity. Also the space complexity over here would be order of 1. Cool. Now let's try to code it up. So let's go to the code. So over here I've already written a small code. This should help. So I'm checking is n a prime number. So what I'm doing is if it's less than or equal to 2. So special case I think I forgot to discuss is that 1 is neither prime nor composite. So this is something you need to remember, that 1 is neither prime nor composite, 2 is the first prime number, right? So if it's less than or equal to 2, then I'll simply return false. If it's greater than that, then I'll start a loop from 2 to root of n. So it's the other way of calling root of n, because I'm saying factor into factor is less than equal to n, or in other words factor is less than equal to root of n. Cool. So I'm checking for all the factors. If the factor is actually dividing n, then in that case I can return a false. If it's not, then I'll return a true. Cool enough. With that, factor is completed, right? So what about sieve of Eratosthenes? I think most of you would have heard it. So let's call it Eratosthenes. I don't know what the exact spelling is, but let's call it as. So what is sieve of Eratosthenes? So now let's say I repeatedly ask you to calculate whether a number is prime or not. So right now we are taking order of root and complexity to check if a number is prime or not. And let's say I give you order of x queries, right? And in each of those queries I keep asking you that tell me if a number n is prime, if a number b is prime, if a number a is prime. Then in each of these queries you'll have to run this particular complexity logic, and this might give you a TLE if n and x are both large number. Let's say I give you 10 to power 5 queries, right? And over here then n is also 10 to power 5, right? Then it might give you a TLE, or let's say n is actually 10 to power 10. Then in that case this might give you a TLE. So there's a better way of doing it. If we are having multiple queries, or we repeatedly want to check the primality for different elements, then we can make an array and we can store it. So how do we do that? So array and storing is pretty easy, but how do we do that thing efficiently? So what we say is that if a number a is prime, right, then for all of its multiples, so the multiples of a would be a firstly, then a into 2, then a into 3, a into 4, and so on, right? If a is prime, then all of these numbers are composite definitely, right? So what I'll do is, starting at a, if a is prime, I'll make all of the multiples of a composites, right? So let's say these are the multiples of a, so I'll make these numbers composite. Also, this particular loop of making the number composite would only be followed for the numbers which are prime, because for the composite numbers its multiple would already have been covered. For example, let's say I start with 2, so I say okay 2 is prime, so I'll make 2, not 2 but 4, then other multiple is 6, then 8, then 10, 12, 14, 16, 18, 20 as composite numbers. I'll mark them composite. So then I'll reach 3. I'll say okay its multiples are also composite, so I'll mark 6. So 6 was already marked composite, no worries. 9, 12, 15, 18, 21. I'll mark all of these numbers as composite. Then I'll reach at 4. Now at 4 it has already been marked as composite number, right? It has already been said that 4 is not a prime number. So for 4 I'll simply skip. As soon as I'll see that it has already been marked as a composite number, I'll skip that. Now why is that the case? Because when I was marking 4 as a prime number, when I was marking 4 as a composite number, I also marked its multiples as composite. So the multiples of 4 are 8, 12, 16. So you can say that 8, 12, 16 have already been marked as the composite number itself. So there is no need of running this loop for 4 again. Then I'll go for 5. So I'll check if 5 is a prime number. Yes, 5 would have been a prime number by now, or it wouldn't have been set to a composite number. So I'll say its multiples, that is 10, 15, 20. I need to mark them as composite. Then for 6, so for 6 it's already been set to a composite number, so I need not do anything with that. For 7 I'll say okay 7 is a prime number, so I need to mark it. So what's the benefit of this? So we are actually reducing the redundant checks. So I'm not saying that for every number. So for every number I'm not running this loop. If a number is already composite, I'm avoiding this loop. The number of prime numbers also are pretty less compared to composite numbers. So my overall complexity decreases and the overall complexity becomes order of n log n. Saving these values for n numbers, or like computing the primality testing for n numbers, is now done in order of n log n, and I can save this data in a hash map or a vector, like wherever you want to store it. And then for a lookup I only need an order of one time complexity. So this actually saves a lot of time. Now let's look at the code for this. So this is the pre-written code I have for sieve. So I've declared a prime sieve. This basically says that if a number is prime or composite, I've taken a big number, it's 10 to the power 6 plus 5. Now for all the numbers, initially I'm assuming that all the numbers are prime, right? So initially all are prime. Then I'm setting 0 and 1 as composites. 1 is not neither prime nor composite, but I don't want to consider it a prime also, so that's why I'm like marking it as 0 over here. Then I'll be running a loop from 2 till the last element. Then I'll check if a number is prime, only then it makes sense to continue this loop, right? To like run this particular loop. So if a number is non-prime or it's composite, then I'll simply continue, or I'll not run this particular loop. Okay, so now if the number was prime, for all of this its factors, the factors of I would be I into 2, I into 3, I into 4, and so on, right? So over here I'll say for j is equal to 2 till j into I is less than size, I'll keep increment my I, and for all its multiple I'll set them to composite numbers. And after that, let's see it in practice actually. So let's firstly check for prime numbers. I haven't actually tested it, so let's test it. So let's say int num, let my num be anything. This is a very random number I just stored over here. Now I'll say if is prime num, then I want to print prime number, else composite number. Cool, let's run it. Okay, so it told that it is a composite number. What about 1 in 9 plus 7? That is a well-known prime number. Let's look. Let's check for that. 1 in 9 plus 7. Okay, so it says that 1 in 9 plus 7 is a prime number. What about 1 in 9 plus 11? This actually should be divisible by 3. So yeah, it says it's a composite number. Now let's try to use the prime sieve itself. So let's say firstly let's call the prime sieve. I'll comment this code out. Then let's say build sieve, call this method. After that, let's check the values for the first 20 numbers maybe. Okay, so firstly I'll print I, then I can say prime sieve. Good enough, let's try it out. Okay, so it's saying that 0 is neither prime nor composite. We knew that. So after these values, 2 is prime, 3 is prime, 4 is a composite number, 5 is prime, 6 is a composite number, 7 is prime, 8 is a composite number, 9 is a composite number, so is 10, but then 11 is prime, then 13 is prime, then 17 is prime, then 19 is prime. I can actually extend it. I can extend it to any number you want, but then it would become very large, I'll say. So let's test it. Okay, so for any random number we can choose. Let's say we'll stop at this number. So it says this has been set to 0. That means 1654 is actually a composite number, but 1657 is set to 1. So that's why we can say that 1657 is a prime number. Cool. With that we understood two concepts, that is prime numbers and the sieve of Eratosthenes. Over here what I'm calling a prime sieve is also called the sieve of Eratosthenes. There's nothing in the name, you just need to remember that what's the complexity of this particular algorithm. The name itself isn't that relevant. So let's move ahead to our next topic, that is GCD. So what does GCD mean? It's a simple topic, I won't need my iPad to explain that. So GCD means for okay, so for every number you have several divisors, right? So for example, in case of 12, the divisors are 1, 2, 3, 4, then 6, then 12, right? What about in case of, let's say, maybe 47 or 45? In case of 45, the devices are 1, then you have 3, then you have 5, then you have 9. After that you will be having, okay, 9 into okay, 9 into 5, 3 into 15, right? Okay, so these are the devices of 45. Are there any common devices between the two? Okay, so over here it's the one is always a common divisor between any two elements, but we have to check the greatest common divisor. So is there any other common divisor over here? Yes, 3 is a common divisor. So over here GCD would be 3. So GCD basically is the greatest common divisor, that common divisor, or in other terms it's the greatest value as a divisor which is present in both the numbers. So now let's try to check it further. Let's try to firstly verify its claim. So in order to implement GCD, you don't need to do anything. There's a built-in functionality that you can use by writing underscore underscore GCD. So you can provide it with two numbers and it will calculate the GCD for that. So let's check the GCD for 12 and 45. Cool. So it's giving the GCD of 12 and 45 is 3. So over here you can see that 3 was actually the greatest number. That was the divisor for both these numbers. So let's try to give it some other more elements. Let's call this. Okay, so for these two numbers, these are actually very big numbers. I'm not going to generate all the divisors for them, but for these two numbers, 49 was the greatest common divisor. Now, why is GCD important? GCD actually comes in handy with a lot of mathematical stuff. So whenever you will be solving questions on Codeforces or on problem solving questions on LeetCode even, GCD would come in handy. Now if I try to explain the use cases of GCD, this video is definitely going to get too long, but I'm just accommodating you with the general idea of what a GCD is and how do you use it. So I think this makes the concept of GCD clear. So let's move ahead to binary exponentiation. So what's binary exponentiation? So this also is not a tough topic. Now let's say I ask you to calculate power of 2 to the power 10. So what would you do? So a simple thing to do is that 2 into 2 into 2 into 2. You'll just do it 10 times, or I can say I'll run a for loop and I run it 10 times. I plus plus, right? And over here, okay, let the result be 0 or result be first, right? And the number for which you are exponentiating it, let it be, let's say, 2, right? And then each time you'll be multiplying the result with the number itself, and then you will print the number. Let's check it out. Okay, so you multiply 2 10 times and you got 1024. Let's try to multiply it by more. Let's try to multiply it by maybe like 20 times. Okay, so you get this particular value. You can keep on doing it, but there's a problem with this. The problem is that in order to calculate the exponentiation, so let's say it's power of x comma y. By x comma y I mean that for we are multiplying x y times. So it would be x into x into x into x, so on till y times, right? The time complexity you're requiring for this is order of y, right? We want to reduce it. We don't want to do it in order of y time. Maybe something like a logarithmic complexity is better. So can we do that? Yes, definitely we can do that by something called binary exponentiation. So binary exponentiation can be easily performed with this scenario. So what I'll be doing is, over here what I was doing, that I was repeatedly calculating the values. Rather than that, what I can say that, okay, so I know I have to calculate 2 to the power 10. Now 2 to the power 10 is similar to 4 to the power 5, right? So rather than multiplying 2 10 times, I can say I can multiply 4 5 times. What more? I can say that I can 4 to the power 5 can also be written as 2 into, okay, sorry, 4 into 4 to the power 4, right? So I can say it can be written as 4 into 16 to the power 2, right? Or this can be written as 4 into, you can multiply 16 by 16, there's no point, so you can simply say it's equal to 4 into 16 into 16. Now how many computations did this take? over here if we're directly doing it, we require 10 computations. But if we used binary exponentiation, so we required only, okay, so this was one computation, so one computation was required over here, then another over here, then one over here. Yeah, that's it. So only 3 computations were required in total. So we can use this fact. So we don't want to recompute things again and again. We just want to divide the power by 2 if it's divisible by 2. If it's not divisible by 2, we'll firstly multiply the value, so that the power becomes a even number and it's divisible by 2. Let's get on to the code to understand it further. So firstly I'll be initiating my result value with 1, and then I can remove this because right now we have not studied the concept of modular arithmetics. So then I'll say while my y is greater than 0, or y over here is power, while my power, remaining power, let's say remaining exponentiation, expo is greater than 0, I'll keep performing this. So what I'll perform, so firstly I'll check if my power is odd, right? If the power is odd, then in that case I'll have to multiply the value x with the with the result. I'll do that. Then I'll divide my power by 2, right? And then I'll make my x equal to x into 2. That's exactly what I was doing in the sample over here. So with that I'll be able to calculate the power. Let's try to see it in practice now. Let's try to calculate it for something. So let's call power of maybe 10 and then 214. So we are multiplying, or let's call it 34. Let's give it a weird numbers. Cool, let's try this. Let's print this number. Cool. So over here I got my answer with that. One more thing I can do is I can actually show you the number of operations that were required. So let's even do that. So let's set a operation equal to 0, and then in the loop I'll keep increment my OP, and at the end let's try to print the number of operations. Okay, now let's try it again. Okay, so over here you can see that it had to be multiplied 144 times, but the number of operations it required, or the number of computations were of the order of 8 only. So it's actually a logarithmic operation. So 2 to power 8, or in other terms you can say log of 144 is somewhat equivalent to 8 itself. So this computation is the order of log n operation, and we achieved what we wanted. Had I multiplied it directly in this way, I would have got a order of n complexity, but using binary exponentiation I get a order of log n complexity. Cool, with that even binary exponentiation is done. Let's talk about modular arithmetics. So what is modular arithmetics? Now this is going to take some time. Let me show my iPad to you. Cool. So let's discuss this over here. So what happens is that if you have a number x, let's say, right, and you divide it by some number, let's say y, there might be some remainder. So a remainder could be 0, or there could be a non-zero remainder you can have. Now whatever remainder you get by performing this, it's actually called the modulus of x mod y, or you can say x mod y is giving you this value. So it's just a fancy way of saying whatever remainder you get. Cool. So this is basically modulus. But now why is it interesting? It's a very easy concept, right? So now you can actually multiply some number, let's say x into z, then you can take a mod y, you can have the right values, you can actually add two numbers up and then take its mod, you'll still have a good value. But what if you divide two numbers now? Now let's say I say that x divided by z and I take its modulus. In other scenario, I firstly take the modulus of y and then I divide it by z. The problem is in these two scenarios the answers don't match. Now for the proof you can Google it up if you want. The proof isn't actually required for this. But so let's just take example to validate this claim. So what I'm saying is, let's say x is 6, right, and my z is 2. Cool. X is over here 6, z is equal to 2, y let's say is 5. So what's the value of 6 divided by 2 mod 5? So this would be 3 mod 5. This would give me a value of 3, right? How about x mod y into 1 by z? So x mod y would be 6 mod 5, that would give me 1. Now if I multiply it by 1 by 2, I'll get a value of 1 by 2, that is equal to 0.5. Now these two values are not equal. So what's the workaround for this? How can we get rid of this problem? So the problem is not doing division at all. So instead of division we can do multiplication, right? So for every number there exists a modular inverse. So for a number x, right, modular inverse is, let's call it inverse of x. It is such that if I multiply x by inverted x or modular inverse of x, right, and then I take its modulus with whatever number I was taking. So over here the modulus was being taken by y, right, and if I take its modulus, then I'll get a 1. This is the simple definition of modular inverse. Now why is it useful? How can we use it over here in this scenario? So what I can say is that if I wanted to divide my x with a number z, right, and then take its mod, instead of doing that I can say x multiplied by inverse of z. I'll also multiply z by inverse of z. I can like multiply numerator and denominator by the same number. Over here I'm multiplying it by zz, inverse of zz. Cool. And then I'll take a mod y. Now if you remember, z into inverse z has to be 1. So this would become a 1. So I'm left with this only. Cool. So now we are not performing any divisions. So at the end even our answer won't be faulty. But how do we calculate this? So most practical purposes, you can actually use the Little's Fermat theorem or Fermat's Little theorem. I don't know which way it's pronounced. Okay, so Fermat's Little theorem, let's call it that. It states that if you want to calculate, okay, so if you want to calculate the inverse of x modulus n, then it would be equal to power of x n minus 2. So basically multiplying x into x into x up to n minus 2 times. This would be the answer for inverse of x. But this is only relevant when your n is a prime number. So just to sum it up, I think it was easy, but still just to sum it up, the first thing is that n is a prime number. Then inverse of x mod n would be power of x comma n minus 2. So basically multiplying x n minus 2 times. This is called your Fermat's Little theorem. Let's see this in practice. Cool. Over here I do have the code for Fermat's Little theorem. Where did it go? Yeah, over here. So for calculating the modulus inverse of any number, I'll just return the power of n comma p minus 2. Over here p is actually the mod I was taking, so yeah, it remains the same. Let's try it out for some number. Let's say I want to calculate the mod for, let's say, call it any num. So int num is, let's say, 10. I want to calculate its mod inverse. So mod inverse of 10 is equal to mod inverse, the function I had, num. Then I'll say num, okay, so I'll say mod inverse is, okay, mod inverse would be printed over here itself. Then I want, okay, so let's firstly do that. Let's proceed with the rest of the stuff later. Okay, I'll have to say mod int, sorry. Okay, so the modulus inverse of 10, it's saying is this particular value, so I guess it's something in the millions maybe. Cool. But how do we verify that the answer is correct? So the basic definition of modulus inverse is that if we multiply this number with 10 itself, then the answer we should be getting is 1, right? So let's try to do that. Okay, over here I'll multiply it by 10, right, and then I'll have to take a mod. So the mod would be taken by mod itself. Let's run this up. Cool. So over here we're getting that the Okay, operations is still being printed. I want to avoid that. Okay, so let's remove this. Cool. So over here it's saying that the modulus inverse of 10 is this particular value, and when I multiplied this by 10 and I take a mod operation, then I get a value of 1. Let's try it with some other numbers. So let's try with this number. I don't even know what its modulus inverse is. So okay, over here I had to do the number. Cool. Cool. So the modulus inverse of this particular number is actually this, and when we multiplied the same number uh, by its modulus inverse and take a mod, then I get a value 1. So cool. With that, even modulus inverse is clear, and I hope you got it, like where and when we'll be using it. Let's jump to the last topic, that is combinatorics. I hope you have already watched the video which I told. If you haven't still watched that video, go and check that video out. It should be on the I button, because before without knowing that concept you won't be able to proceed over here. So cool. So let's talk about NCR. So NCR is basically combinations. So in combinations, first we'll be doing the basic checks. So if the ways I'm going to check is actually less than the total number of things we have, then I'll return a 0. In case my R is 0, then I'll the only possibility is a null set, so in that case I'll simply be returning 1. Then over here I am actually calculating the factorials, so even the factorials are important. So factorial of 0, as discussed in the video, is actually 1. This is a special case. Okay, cool. Then we'll be going from 1 up till n. What we'll say is that factorial of I is equal to the multiplication of factorial of I minus 1 and the current number, which is I, and then we'll be storing these values in this vector that is named factorial. Now what about NCR? So NCR can be easily calculated. So NCR value is basically n factorial by r factorial into n divided by n minus r factorial, right? So since I want to avoid division when I'm talking about larger numbers, because I have to take a mod as well, so we'll be using the concept of modular inverse. So we'll be saying that the value of NCR is actually factorial of n into modulus inverse of factorial of r into modulus inverse of factorial of n minus r, which is equivalent of saying that it is n divided by r, n factorial divided by r factorial divided by n minus r factorial. So yeah, cool. This is the way we calculate NCR. It requires some kind of prerequisite, but that video I had already made was pretty detailed. I hope you understood it from that. Let's calculate the NCR for any values. So let's say my n is 1 2 3, and let's say my r is 1 3. So let's calculate NCR for this number. We'll get the answer over here. Okay, it gave an error, but why? Okay, C is capital. Let me capitalize this. Cool. So this large number is the number of ways, or the number of ways in which you can select 13 elements from a set of 123 elements. Let's try it for some smaller number so we can actually validate it. So what's 5C4? 5C4 is actually 5. You get it over here. What's 3C? Okay, 3C1 is also known. Let's 3C1. 3C1 is actually 3. What is 4C2? Okay, so 4C2 is actually 6. So yeah, we validated that the answers are correct. I hope you understood the solution and you don't have any doubts in this. But still, if you have any doubts, please let me know in the comment section below. For this video, however, I won't be posting any questions or any homework section, because mathematics is not directly asked in questions. Most of the times it's the case that mathematics serves as a tool to solve the questions. So there are more concepts required generally in the questions other than mathematics as well. So it's really tough to find questions that just require some sort of mathematics and no other concept is included. So for this, I'll be giving a break on the questions either from LC or Codeforces. But yeah, if you get any nice question or an interesting problem, you can definitely share in the group with all of us. It would make it better. So like even we could see that problem and we could discuss it on the Discord server itself. Cool guys, thanks a lot for watching this video. I hope you liked it. Stay happy, keep coding. Bye bye.